This portion of the lecture will be over the preparation of carboxylic acids and some of their reactions. And we already know a few things about carboxylic acids. We started talking about acids as products of the oxidation of alkenes back in chapter 8, and that occurs whenever you have at least one vinyl hydrogen. Remember, the vinyl hydrogens are the ones that are directly attached to the carbon of the double bonds. And so in this example I have two R groups on this carbon, but one vinyl hydrogen and R group on the other carbon. So I will get a ketone from the one end, and the other end can make a carboxylic acid. It's going to go by way of an aldehyde, but under these conditions, aqueous permanganate, it will further oxidize the aldehyde to the carboxylic acid. And we talked about that recently when we were talking about aldehydes and ketones in chapter 19. We also learned about making carboxylic acids by the oxidation of, in the aromatics chapter, on aromatic compounds that have side chains on them. And so the benzylic position, which is the one away from the benzene ring, as long as there's at least one benzylic hydrogen there, then you can oxidize that to a carboxylic acid. Now in this particular example, I have two benzylic position carbons, and so everything gets oxidized away except for those two carbons. The benzylic position carbons directly attached to the ring stay, and everything else goes. And so we can make the dicarboxylic acid out of that, and the rest of the carbons are lost. And we use permanganate for that too, and just heat it up, and it gets oxidized industrially. They have other ways to do that besides using permanganate, but they would get the same kind of results. So in chapter 17, which was the chapter about alcohols, we learned that we could oxidize primary alcohols to carboxylic acids, and we have several ways to do that, but usually they use chromic acid, which is just chromium trioxide dissolved in sulfuric acid, and that will create chromic acid and oxidize your primary alcohols to carboxylic acids. Remember, carboxylic acids have to be at the end of a chain, so you use a primary alcohol to get there. And we also talked about oxidizing aldehydes in a little more detail in chapter 19. So we've talked about oxidizing the alkenes, and that went by way of an aldehyde, and then it kept going, and so we've kind of known about that sort of thing for a while. So aldehydes are subject to oxidation by chromic acid, which is what you get when you dissolve the chromium trioxide in sulfuric acid, or permanganate in the aqueous acid solution. All of those things, and even oxygen and air, will oxidize aldehydes to carboxylic acids. Something else that we kind of talked about just briefly in chapter 19 was the hydrolysis of nitriles, and we talked about it in the context of making cyanohydrins and why would we be interested in those, and that was where you added the elements of HCN to the double bond oxygen, the carbonyl of the aldehyde or the ketone. You would make a cyanohydrin. So the same carbon, the carbonyl carbon, then has a cyanide group on it and an OH on the same carbon. And so we talked about the hydrolysis of those to alpha hydroxy acids, which are used as cleansers and are natural fruit acids. So we can make nitriles other ways, and we'll talk about that some more a little bit later in this chapter when we concentrate on nitriles. But at this portion, we're interested in turning nitriles by hydrolysis into carboxylic acids. And hydrolysis does not change the redox level of the carbon, and it's also not changing the number of carbons. It's just changing the state of the carbon in question. So when we add aqueous acid and heat it up for a while, then we can hydrolyze this nitrile to the carboxylic acid. Now when you do this in acid, your other product is ammonium ion, and a free acid is produced directly. But you can also do these kinds of hydrolyses in base, but because the product you're going to make is going to be an acid, if you're in basic solution, it would come out as a salt. Remember, carboxylic acids react with sodium hydroxide to make a salt. So you'd have to do a pH adjustment at the end. But either acid or base hydrolysis, heating it up in the aqueous acid or base solution for a couple of hours will hydrolyze nitriles to the carboxylic acids, which are really their parents, because nitriles are technically a derivative of carboxylic acid. Another thing that we've used in the past we can use a little differently is the Grignard reagent. And we've talked about Grignard reactions where we talked about having an aldehyde or a ketone react with a Grignard reagent. Remember, when you make the Grignard reagent, the carbon that's originally bonded to the magnesium, like in this case, this carbon has positive character. When we react it with the magnesium inserts itself in between this carbon and bromine, and ultimately the carbon then has negative character. The bromine has a lot of positive character, and so both the bromine and the carbon get negative character, and that effectively reduces that carbon. And we use that as a nucleophile on aldehydes and ketones to make larger alcohols, and we studied that in Chapter 17 and revisited that in Chapter 19. And so if you look at CO2, it's kind of like a double whammy carbonyl. And so it turns out that a Grignard reagent will react with the carbonyl of the CO2, but only once. And the reason it only reacts once is because when you take the pair of electrons that you've got from this carbon that's now attached to the magnesium, and you make a bond with this carbon, which has positive character, it's going to push the electrons onto the oxygen, and then it will precipitate as a magnesium salt. And then it can't react again. And so you get one of those things on the in place of the, or added to this carbon, you get this new carbon. It's a magnesium salt. It precipitates out, and then when you put in the aqueous acid, then it protonates it, and you get that to go into the organic solvent, and the inorganic materials stay in the aqueous acid. And so this is a very nice way to incorporate a source of CO2 from dry ice, for example, is really the most common way you get the CO2, and you incorporate that new carbon into your molecule. Now, if you think about it, both the nitrile reaction to hydrolyze the nitriles to the carboxylic acids, if you think about it, nitriles probably came from an inorganic source. So we've talked about adding HCN, for example, to aldehydes and ketones. We can also make nitriles from SN2 reactions. And so those nitriles, we talked a little bit about the cyanide ion as a nucleophile in Chapter 11, which is where the SN1 and SN2 mechanisms were. So you've got basically an inorganic source of the carbon in the form of the nitrile or cyanide ion, or you've got the possibly could be considered inorganic source of carbon from CO2 if you choose to do the Grignard reaction. And both of those two methods of making the carboxylic acid have some good and bad points. For example, if you wanted to make a nitrile that you would then hydrolyze to a carboxylic acid, you might be doing an SN2 reaction, and the limitations of SN2 is that the carbon of the substrate can't be too crowded. So that could limit your possibilities. Also, you've got to do the hydrolysis, which is going to be in strong aqueous acid or base, and heating it up for a period of time. There may be other functional groups in your molecule that wouldn't survive that kind of process. On the other hand, if you want to do a Grignard reaction to make your carboxylic acid, there are also limitations with that somewhere else in the molecule there can't be something that would also react with the Grignard reagent. For example, you couldn't have an aldehyde or a ketone group somewhere else in the molecule where you're trying to create a Grignard functional group. So these two reactions, nevertheless, could be thought of as kind of partners, as one or the other of them ought to be a good choice a lot of times to make a carboxylic acid. So we'll look at these factors in considering an example like this. So if you want to make this molecule and you want to do so by adding the one carbon to what had been an alkyl halide, then we're going to have to look at creating this bond right here. And so we want to know what's best, and so we're looking at the degree of this carbon. Before we make this bond right here, the degree of this carbon is tertiary. So if you start thinking, well, could I use that in an SN2 reaction, then hopefully you'll remember that the answer would be no, not really, because tertiary carbons don't do well in SN2 reactions. On the other hand, we could do a Grignard with a carbon attached to a halogen here and make that into a Grignard reagent and then add CO2 to that, because it didn't matter what the degree of the carbon was when you were trying to do Grignards. So I would choose the Grignard reaction, and so remember the way that works is you add magnesium followed by CO2 and then an aqueous acid workup, and you started out with an alkyl halide, so you just have to put a halogen in the place of where you want the CO2 to go, and so that would work nicely for making this molecule. Alright, so let's try that again. So in this case, again, if we're trying to create the carboxylic acid from, adding this one carbon group, then we would say, well, if we wanted to make this bond right here, and we were trying to do the same sort of thing we just did with a Grignard, we've got this other group down here, this ketone, which would also react with a Grignard. It might be that as soon as you started trying to form the Grignard here, it would react with another molecule with the carbonyl on a different molecule, or depending on how many carbons it might try to cyclize. Whatever, you're going to have problems with this ketone in your molecule for trying to do a Grignard. So what can you do? Well, you could get a nitrile, a cyanide group on in this place and do the hydrolysis. In other words, you need this molecule. So then you start, well, okay, where do I get that from? And I told you we would review this. You can do an SN2 reaction. So if you look back in Chapter 11, the cyanide ion was a potentially good nucleophile for alkyl halides that aren't crowded. So this is a primary carbon. We can react with this. Now, one of the things that's going to bother you a little bit about this is you say, well, what about that carbonyl? Don't they also react with nitriles? And so really the best thing would be to disguise this carbonyl and hide it in the form of an acetal. And we talked about that as a protecting group in Chapter 19. So you could make the acetal with alcohols, and this one will make the cyclic acetal, and there you go. So now you've got this cyclic. So now it doesn't matter. You can either go to use the cyanide ion and go to the nitrile and then do this reaction, and actually this aqueous heat will take this guy off at the same time as it hydrolyzes the nitrile. Or now that you've got your ketone protected, you could do the Grignard even. So either one of those, by protecting this ketone, gives you more options. And just for the heck of it, you might want to practice nomenclature. Remember how the nomenclature rules go. The carbonyl has to be carbon number 1. So at 1, 2, 3, 4, at the 4th carbon I have this carbonyl, which is a ketone, and we have a total of 5 carbons. So carbon number 4 is a ketone, and the group name for that is OXO, or oxo. So this is going to be 4-oxo, and the 5 carbon chain is pentanoic acid. Now, we're not going to do a lot of reactions of carboxylic acids in this chapter. We're going to do most of them with respect to making derivatives in the next chapter. But one of the things we've already talked about was the acid-base reaction of carboxylic acids with reasonably strong bases like sodium hydroxide in aqueous solution. You can make the sodium salt of the acid. And this is important for several reasons, which I had talked about previously, including purification or titration. The long-chain carboxylic acids are, when they're made into salts, are soaps. So there's a lot of reasons why we're interested in this reaction, and it's also been used. If you use a weaker base like sodium bicarbonate solution, you can tell the difference between strengths of acids. So if you're looking at something like acetic acid, is, the typical carboxylic acid's pK is around 5, compared to weaker acids like, say, phenol, which is, remember that was the aromatic ring with an OH on it. Its pK is about 10. So phenol would be soluble in sodium hydroxide because it's acidic enough to react with that, but it's not acidic enough to react with sodium bicarbonate. And so that kind of differentiation has been used to separate acids relative to their different strengths, depending on which one they would dissolve in. And so that's kind of historically important, but it could be used to help separate these molecules if you have mixtures. So what else can we do? Well, we know that from that overview section, that was the chapter 18 3/4, or it wasn't labeled as a chapter. We talked about kind of the overview of how these carbonyl compounds would react, and the thing that we saw mostly in chapter 9 was addition. So we had really good nucleophiles would react with the carbonyl, make the tetrahedral intermediate, and then you could protonate. You could get an addition product that way. Or if we had a weak nucleophile, we could protonate first, get the resonance stabilized species, and then the moderately good or weak nucleophiles would react with that, and you'd still get the addition product. And this was what commonly happened with aldehydes and ketones. And sometimes, further things happen. That was basically fundamentally what was going on there, because whoever this Y group was usually not a good leaving group in the case of aldehydes and ketones. So in chapter 21, what we're going to see dominating is nucleophilic substitution reactions, in which case the nucleophile can be just adequate. It doesn't even have to be a full anion, because these Y groups are things like halogens or another oxygen or nitrogen group. So more electronegative stuff is going to make these carbonyls have more positive character, and these Y groups are going to be better leaving groups. So just adequate nucleophiles will react, and then when you get your tetrahedral intermediate, the oxygen says to the carbon, do you want to remake a double bond? And the carbon says, does anybody want to leave? And a lot of these Y groups will then go ahead and leave. And we'll be looking at what all those groups are when we get to chapter 21. But ultimately, the product is you've had a nucleophile take the place of this Y group that was leaving. Now, in the case of carboxylic acid itself, Y in that case is just an OH group. And so we know that OH groups are not very good leaving groups by themselves. And so carboxylic acids aren't very good at doing this particular reaction. So one of the things that we need is to manipulate that OH into being a better leaving group. We had some situations like that back when we were talking about alcohols and so on, that in chapter 11 and chapter 17, if we could turn the OH into a better leaving group, then we could get that oxygen off of there. And the same thing is going to be true with carboxylic acids themselves, and that's why a lot of the reactions that lead to their derivatives are really one derivative to another, and we really don't study that in the context of the carboxylic acids themselves so much as with their other derivatives in chapter 21. What we can do is we can remember that these are acids, and so they do react with bases, and that if we wanted some kind of a nucleophile, we may have to deal with the fact that it's an acid and have extra nucleophile in there to take care of the acidity, and then have enough left over to still be a nucleophile. And of course, the other thing, which we just talked about, is making the OH be a better leaving group by changing it into something else. And so that's one of the things that will happen, and we'll see a little bit of that in this chapter, but like I said, mostly in chapter 21. And we'll also see some ways to operate on a carboxylic acid at the alpha position in chapter 22, but again, it's not going to really be directly on the carboxylic acid itself. It's going to be by way of one of its derivatives. And I want to remind you again about where we are in the redox scheme. So we're talking about carboxylic acids and their derivatives are all at essentially this redox level. So almost to the oxidation, the most highly oxidized form of carbon, but not quite. And if we're going to change from one carboxylic acid to its derivative, we're not changing redox levels. But we have in the past talked about reduction, and we've talked about reducing carboxylic acids to alcohols, and we've talked about reducing esters to alcohols, we've talked about reducing esters to aldehydes, but one of the things we won't ever talk about is going by reduction from an acid and being able to stop at an aldehyde. You have to go through a derivative. You can't go directly from an acid and stop at an aldehyde. And as part of this reduction, we talked about these various derivatives of boron and aluminum. Remember, these are the blah blah hydrides, and so they delivered hydrides, and the sort of the parent molecules are stronger than the derivatives, and the aluminum version is always stronger than the boron versions. And remember, we never use alane in organic because it's way too flammable, but just for reference sake, in terms of how these things fit together, it's there to sort of help you see that. And so the boron and the lithium, borane and the lithium aluminum hydride are about the same strength, and we need something about that strong or stronger to be able to reduce the carboxylic acid derivatives or the carboxylic acids themselves. And diacetyl aluminum hydride was introduced as a way to stop at aldehydes because it only has one hydride to deliver and it's crowded, and so that also helps it. So we have seen the reduction of carboxylic acids in chapter 17 to make alcohols, and we used the borane or the lithium aluminum hydride to do that, we could not use sodium borohydride because it wasn't strong enough. And the way that works, we didn't really talk about it in the alcohol chapter, but the way that's going to work is, so your hydride, lithium aluminum hydride has 4 hydrides to deliver. And so really you're going to have an acid-base reaction first. And that's fine because you have plenty more hydrides. And so then you get this anion which will complex with the aluminum and then essentially make a kind of covalent like bond here, and then the second hydride can come along and now it can be a nucleophile, and so you'll get this tetrahedral. Well, now both of these oxygens have negative character, so now both of them can be complex with the aluminum, and at that point you've done nucleophilic addition. So you've added this hydrogen, so you've got your tetrahedral species right here. Well, this can lose the aluminum, reforming a double bond here, and so one of these oxygens goes off with the aluminum. So that made that oxygen be a good leaving group because it's going off with this inorganic stuff. And then you're reforming the carbonyl. So at this point, essentially you've substituted a hydrogen. So right here, this hydrogen has taken the place of this OH. But you notice that the OH didn't come out as OH. It came out as hydrogen molecules and aluminum oxide stuff. And the aldehyde, so at that point you're finished with the nucleophilic substitution reaction that you get for carboxylic acids and their derivatives. Now we know that aldehydes are also able to be reduced by lithium aluminum hydride. So another hydride, we've got some more left in our original lithium aluminum hydride. Remember, it had 4 of them, so we used one here, we used one here, we've got one here, and so we can go and do addition. So we take this nucleophile, react, the electrons go up here, and now at this point the oxygen says to the carbon, you want to make a double bond again, and now there's no good leaving group, and so it just sits here, and it might still also be complex with the aluminum, but it's just going to hang out until such time as you put in the aqueous acid, and then that will protonate it. And so that we've condensed this stuff up to put these 2 hydrogens in here in line, and the new hydrogen is right here. So this hydrogen comes from the aqueous workup, and these 2 hydrogens come from the lithium aluminum hydride. I didn't color code them. So that's really how that process is going. So we used up most of the hydrides available from one lithium aluminum hydride molecule. So that was a reaction that we knew about already. We just hadn't really talked about it in that much detail. So pretty much the rest of the reactions of carboxylic acids are going to involve their derivatives, and as I've said several times already, we will look at those in chapter 21. So now what remains to do in this chapter is to look at nitriles. Even though nitriles are really carboxylic acid derivatives, they don't look much like the others, so they're going to be covered in this chapter, but I will talk about them in chapter 21 in terms of how they fit into the larger picture. You'll hear about them occasionally there also. And that's the end of this section of material.